test 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 test
ว่าเอาคือถ้าเป็นการดูต้องพูดกับออกที่ไม่ได้นะครับผมไม่ได้ตามเราปลาหัวติดสติ๊กเกอร์ไรซ์ด่าแล้วเชี่ยอะไรวะเนี่ยพูดอยู่ในมือไม่สนุกอะไรวะเนี่ยงงคุยอะไรกันอยู่เนี่ยไม่ได้ใช้นานทำไงวะเนี่ยโอเคเปิดวิดีโอไว้ก่อนก็ได้เสร็จแล้วก็เดี๋ยวให้เดินตาม
Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Good afternoon, everyone. Welcome to Tah Poe Seminar Series 57 and talk number 1. Today we have Dr. Sikarin Yoo-kong to tell us about can we describe thermodynamics in the same sense with classical mechanics. Please welcome our speaker.
All right. Okay, thank you very much for introduction. I hope that you can hear me well. I believe in this room. I'm not sure on. Is that okay online? Okay. All right. Okay. So the topic today that I would like to talk about is this one. Actually, Atan Pam mentioned already. Which is actually very interesting because normally in thermodynamics we don't have really kind of the thing that the same sense in the classical mechanics, right? That's why I present this kind of title. And so this talk actually based on this work, right? Action principle in for equilibrium thermodynamics, and also some further development. Okay, you will see later. And this is what I'm going to tell you today. I'm going to start from a basic concept of thermodynamics, and of course, something about to do with the differential form and part independent feature of thermodynamic functions, right? And then, of course, I'm going to mention about basic concept of Lagrangian mechanics, and of course, as well as the Hamiltonian mechanics, right? And I also would like going to mention about this thermodynamic space or contact structure here, which is actually this kind of okay, come back. This thermodynamic space is already was mentioned in the EVE colloquium, the latest one by Professor. I could not remember his name. Anyway, about geometric thermodynamics, something like about that kind of stuff. And then I'm going to point out analog feature between Hamilton equation and the Maxwell equation, right? And then I give you a summary and open problems at the end. Okay. So for simplicity, I'm going to stick with the ideal gas system and reversible process, and of course the equilibrium situation. Let's start with some basic of thermodynamics. We know that actually we have like a standard diagram that we call PVT, right? And for like a system of the ideal gas, we have this kind of equation, right? PV and KBT, right here. And in thermodynamics, you need to define what is your system, right? And what is your boundary, and what is the surrounding, right? And we know that actually this equation is called the equation of state, right? Within given the point on this particular surface, you can get this kind of value, right? This kind of thing. But we don't really have dynamics or equation that could get you from this point to this point. That is the point, right? Yeah. All right. And so there are some various processes actually you can do to get from point 1 to point 2, right here, like isothermal process, which is temperature is constant, and adiabatic process is no heat getting involved into the process, isobaric process, and isochoric process, something. This is kind of example. And okay, now I give you some of example of the thermodynamics, which is actually we could say that this can be actually extended in the differential form. Like the first one, internal energy, you could have this equation. Then there is also a Maxwell equation related to this quantity in this way. And also you could have like enthalpy, gives free energy, and some other potential. Actually, there's more potential you can have, right? This is some of the okay. Again, in this case, the capital N, number of the particle, is being fixed, right? For simplicity. Otherwise, we have more term, right? Like involve the chemical potential, right? That kind of stuff. Okay, and now if we look again on the internal energy here, right, and it's quite trivial that actually the coefficient in front of ds and dv is nothing but these two relations, right? And according to this relation, exactness, right, you could get this kind of nothing but the Maxwell equation, right? And you could do the same trick with some other potential in the list, okay, that I give you earlier. Now, let's talk about it a bit more. What does it mean by having this kind of feature exactness here? Means that actually this quantity, the chain of du, actually depends on the endpoint. Or another way that you can put actually the u is the chain of the u is kind of possess part independent feature, something like that. Okay. And for the cyclic, process, actually, if you start from point 1 and you go up to point 2 and then come back again to point 1, and then you get like a loop here, you find out that actually there is no chain of the internal energy in this way. Yeah, this one. All right. Okay. And now I can apply a Green theorem, right? Okay, I get this equation, and so and now I promote this new quantity dw here to be a two form, right? It's called a differential two form, and then of course I call it a symplectic two form, and I'm going to explain later why I call symplectic two form here. Okay, but we have just remember that actually now this kind of object is called differential two form. Okay. All right. Okay. So then we can geometrically interpret what we have here is that the chain. Where is the pointer? Okay. The chain of this kind of the u along the closed loop here actually give you 0. It means no chain, right? And if you think that actually du is nothing but the vector field, right? Indicated by this blue arrow here, right? It means that along the chain of this kind of arrow along this loop, it gives you 0, that kind of thing. And in terms of thermodynamics, this term represents the heat added to system and work done by the system. That kind of convert to each other, right? Work energy theorem. Okay. And as I mentioned, if you think that if you treat this du as a vector field, the component is of this vector field is nothing but the ds and dv. Okay. All right. So now come to the basic Lagrangian mechanics, which actually I believe everyone know more or less well about this stuff. So let's say that actually we have a set of generalized coordinates, right? And n is number of degree of freedom. And then there is a part here, and then we can define the action, which is nothing but integration of the Lagrangian, right? And you do the variation, right, with the fixed term, right? And you with the critical condition of the action, you could get the Euler-Lagrange equation here. And so this would give you, the Euler-Lagrange equation would give you the equation in motion, right, subject to the initial condition of the system. And of course, this one is give you, what I mean by equation of motion is now you get kind of the dynamics equation explain how your system evolve in time somehow. Yeah, right. Okay. And this is a little bit more fancy stuff. Actually, we have also abstract space that we call configuration space, which is to have the n dimension, right? The same dimension with the degree of freedom of the system, right? And the part is nothing but the map from the real line, right here. And you also have, in this context, you also have another abstract space that we call tangent bundle, which have 2n dimension, right? And on this space, every single point on this space, you can feed into the Lagrangian, and then your Lagrangian is nothing but a map into the real line, right? Yeah. Okay. Now, there is another abstract space we call cotangent bundle. And in this space, we should actually define the function that we call Hamiltonian, right? Which is also acting as a map. Once you feed the coordinate P and Q into this function, it's going to bring you to the real line, right here. And now, P is a set of conjugate momenta as right. Yeah. And in this context, if you there is a connection between Lagrangian and Hamiltonian in this way, they call Lagrangian transformation. And you also have like a set of equations we call Hamilton equation, right? This is the first order, couple first order equation, right? You can use this set of equations by equation of motion of the system, which is going to get the same, exactly the same that you get from the Euler-Lagrange equation, right? And so here is a point, very interesting point. So now the action could, you could write the action in this way, right? And then you can say that actually this bit is nothing but the dA in this way, right? And then now you can see that this is nothing but the differential form, right? Okay. And the special kind of main feature, I would say, for the Hamiltonian mechanics, that actually you need actually the symplectic structure, right? Now, let's recall the relation that I mentioned earlier, this dA in the one form that actually, again, is not difficult to see that the coefficient of d in front of dq and dt is nothing but these two relations here. And according to exactness, you get this kind of equation, right? Which is the first one in the Hamilton equation, right? And if you look at this carefully, and you can see that actually this kind of structure is kind of very, is kind of more or less the same that we have for the internal energy, right? That I mentioned earlier. So now we get one of the Hamilton equation by having this, by working with the one form structure of the action. So we need to get another one, right? So to get another one, I introduce this kind of quantity x here, which is actually s minus pq. Sorry, this s should be a here. Sorry, this one is a typo here. It should be a, right? And then you compute dx, and you get this quantity, which is actually one form again. And by working on the exactness, you will get another equation of the, which is nothing but another one of the Hamilton equation here, right? So, and then is it not difficult to see that actually there is connection between the dA and the dx through this relation, right? And then now I can define the symplectic two form in this way, which is actually, this is the variable, the variable u and v in this way, okay? All right, okay. And of course that we're going to have a Poisson bracket structure as well. Here. And let's put in this way. Normally in standard context, you're going to work with only the first Poisson structure here, right? But this one is not really trivial that actually you could have, but well, you can extend the structure of your system, the space of your structure of your system. You get more one more pair of your variable here in this case. yeah, as I mentioned, this kind of standard treatment on the left hand, on the right hand side, right? On the left hand side is a kind of extended version, which is actually you have 4 dimensions. On the right hand side, you have only 2 dimensions, right? Okay, and so now we come back to part independently feature of thermodynamics potential, which is actually, again, I'm going to work with the internal energy here. So far we know that actually this U, I mean this du here, okay, has symplectic structure, right, as I mentioned. And if we consider this kind of 2 different parts here, and you can, well, you can actually, this one can be rewritten in this way or in this way, right here. And we have to note that the change of the internal energy would amount to a specific choice of the thermodynamic processes, right? Yeah, of course. And the interesting bit is that there is 2 options that you could write du, right? You can pull out ds or you can pull out dv, right, in this way. And now, if you do the first one, do it by pulling out the ds, it means that the v, the volume, will play a role of independent variable, and s will play a role of dependent variable. If you pull out the another way around, if you pull out the dv, it's going to switch the role somehow. Is that correct? I think maybe wrong. Sorry. I think if I pull out the first one, if I pull out the ds, the s would be independent variable, right? Sorry about that. Sorry, it's my bad, right? Sorry. Okay. If I do this, the s will be independent variable, and this is going to be dependent variable, right? Okay. So by doing this, I think in order to capture the part independent feature, of internal energy, I'm going to introduce the action functional, actually nothing but the internal energy itself, okay, by consider this integral along the curve on the SU diagram, SV diagram, and this L is called Lagrangian one form, right here. And what is this kind of fancy L here? It's actually nothing but this one. This is a fancy LV, a fancy LS here. And of course that if you demand the critical condition of the U, right, within working on the variational principle, you will get this kind of equation out of that equation. And we can say, we can prove that actually this relation, I mean, holds on this Maxwell equation here. It means that, so by having this, it means that the independent feature of the U can be captured in terms of kind of Lagrangian description now, right? In kind of, but is not in the very implicit way. But we can say that actually by introducing a new way of looking on the system that we call like a Lagrangian one-form structure, we can capture the part independent feature of the internal energy right here. And this is the proof of that actually you just plug the L in and then you just apply the Maxwell equation and then yeah, you could see that actually it works. And right, okay, so this is the kind of what we get at the end. So upon working on this internal energy, there is a 2D surface of equilibrium state, right? Yeah, we actually with all the quantity defined in this way, right? Or in short, this is might be a better version, right? This is definition of the T. If you have U, you can compute the temperature, right, or the pressure, and this is nothing but the Maxwell equation here. Okay. Right. And okay. So, previously, what I did is that I worked out this equation. I mean, this closure relation from the rational principle. But there is another way that actually we could get this equation actually by looking at this relation. I mean, here, right? You can apply again. This is the one form, and then the closed loop, and then you can apply the Green theorem, right? You get two forms here, right? And then you put it into zero, and you will get inside the bracket. You see the two copies of the closure relation here, right? And again, yeah, you get the closure relation out of this, right? There is another way to get the closure relation. And again, as I mentioned, you could put, you can treat du nothing but the vector field, right? And in this case, this component, the du, your du here, could the fancy L, V, and Ls can be treated as the component of the vector field with the basis again, the basis dv and ds right here. Yeah. Okay. Sorry. So far, we can somehow use a new another language, not the standard language of Lagrangian mechanics to capture the part-independent feature of the internal energy, right? We need the extended version of the Lagrangian description called Lagrangian one form somehow. Okay. All right. Next, there's some more fancy stuff that I would like to talk, which is actually again related to this kind of stuff as well. Now we are going to introduce to you guys about thermodynamic space, or they actually call contact space somehow. Given this 2n+1 dimension, right? This space called this kind of T, right? And there is within a set of coordinates. Here is the set of coordinates here, right? And this size is nothing but a thermodynamic potential, right? And EA and IA are the extensive and intensive variable, right? And I also introduced the fundamental Gibbs one form in this way. And this a pair of this thing called contact manifold, right? And yeah, of course, there is some kind of property that you need, right? And so actually, you could do the map. You could reduce this kind of 2n+1 space to n dimension space we call E here, right? By applying this map, right, in this way. And so, and by having this map, you could also have a pullback of the map, right here. And this space E here is nothing but the equilibrium space of the thermodynamic system, okay? Because you have this equation, right? Gibbs one form, actually equal to 0, right? Let me give you example. So before I give you example, there is another feature that actually, which is actually very interesting. For this thermodynamic space, there is a feature that actually equipped with this space is actually every single point on this space can be explained the physics in the same way. It means that actually it's kind of invariant under the Lagrangian transformation. So you can choose any point on this space to describe your system, and you will get the same physics. That is the thing, right? This is the main feature. Okay. And so this is kind of example. Suppose that the first one, I say that I have Gibbs energy, right? Here is a set of coordinates, E and I, for the Gibbs, right? And then you have the two-dimensional surface for actually this equation holds right here. You have to understand that this kind of very cartoon thing, right? Okay. And for the internal energy, you could have the same, because for the internal energy, you have a different set of E and I, and you're going to have another two-dimensional space that actually this equation holds. Okay. And of course, for the Helmholtz as well, and some other potential as well. But I give you in this picture only 3 of them. Okay. And so let's get back to what we're working on for the internal energy, right? Like a part independent feature that I explained previously, right? But oops, sorry, what's going on? Okay, come back. Okay. So I'm just, what I did is just combine this kind of abstract thing and what I had before together. It means that all the features that explained by having Lagrangian one-form stuff can be put in this particular 2D space, right, for the equilibrium system by having this equation holds right here. That's it. Okay. Okay. And here we can somehow we also have kind of symplectic two form, as I mentioned earlier, right, for the thermodynamic system. And we also have this kind of this is for the classical mechanics, right? This is the dA, which is actually we have the momentum, the coordinate here, and the Hamiltonian at the time, and we can compare the variable from the set of the classical mechanics here, the first row, right, and the second row is the set of variable from the thermodynamics, right, one. You can see that actually this TDS minus PDV and PDQ minus HDT here. And it's very obvious that actually you can build up this table, right? Okay. And so in this case, actually, your V is going to play a role of like a time variable in this case, okay? It's very weird, but yeah, of course, what we have here. And so, of course, and as I mentioned, the description of Lagrangian one form also can be embedded into this abstract space as well, as I mentioned. Okay, and now we move to the Hamilton equation and the Maxwell equation. And now I show you here the right hand side is very basic stuff from the Hamiltonian mechanics here. If you look at this, a couple equation right here on the PQ space here, right. And in the thermodynamics, you also have this two set of couple equation, which is nothing but a Maxwell equation, okay. And you can and in the PV, okay, space. And again, if you compare these two equations, you can set a table, right? This kind of table here to match the variable in this way, okay. And you can see that it's kind of very naively kind of share the same structure somehow. You see, so because on this side, your S going to play a role of the Hamiltonian, right? but it's not really Hamiltonian, right? But it's kind of behave like a Hamiltonian, right? And the pressure is going to play a role of the Q here somehow, right? And the V is nothing but the P here, right? Something like that, okay? And the time variable can be matched with the temperature in this case, okay? All right. And of course that by having this kind of structure, you could have a set of Poisson equation, right? This is from the Hamiltonian. This is from the Hamiltonian mechanics, right? And also you could have from the thermodynamics, right here, to bracket here. And the question is that another main thing is actually we need in the context of Hamiltonian mechanics is a Liouville theorem. It means that what you mean by having this theorem is the area on the space plate must be preserved under the time evolution, right? And this is not difficult to prove because in the Hamiltonian mechanics, well, you can say that there is the bit distribution function we call rho here, right? Actually, nothing but all this point actually in the area that we consider, right? That is kind of distribution function, and you need to see actually all the point on this area is going to be mapped into the new area in this one, right? And so let's say that if you have 10 points in this area, one is mapped into this area, it must be 10 again. That is kind of very naive way to say the Liouville theorem, right? Okay. And by having this, you're going to have like a probability, right, function here, right? And it's going to obey this kind of the equation, okay? So the question is that what about thermodynamics that we have the more or less the same structure. So yeah, could we have like a Liouville theorem in this particular space, big P, big P and big V here, right? So well, of course we can have that. You can introduce this kind of distribution function rho, right, in the same sense that we have in this slide, right? And you also have this kind of probability, right, to find the system in this tiny volume here, right? And you can say that actually this rho is constant along the trajectory of the phase space. You can also have this kind of equation here, but you have to replace everything. I mean, you have to replace S here by the S and the T by the temperature, and then you will get the same. And also you could have the Liouville theorem for this kind of structure for the thermodynamics. That's it. Okay. Let me give you example, right? For again, for simplicity, because I mentioned I'm going to consider for like for very simple system like ideal gas. Then in the mechanic, I'm going to consider for the free particle because it's the simplest system, right? So this is the phase space, but kind of I have also the t direction in this way. We know that actually for the free particle there is a constant velocity or the momentum, right? It means that you're going to have like a line here, right? And this line can be extended in the time direction, then you can get a surface right here. Okay. And so if actually, every single point here, actually there is if you pick any point on this line, you will get the constant Hamiltonian, right? Okay. But I think I need something, but here is kind of one dimension thing. I need something to do with 2 dimensions, then I just vary the energy a little bit, and I will get this picture. It means that I vary E to be E palm. It means that your potential, your P going to change to be P palm as well, right? So you have two lines, right here, and you're going to have two surfaces. If you right, and according if you consider the area in for this area 1, which is actually the first one, and you let the system evolve in time to be at the area in number 2, right? According to Liouville theorem, it means that the number of points in this area must be preserved. It means that number of points in this area must be the same of number of points in this 2. Sorry? Yeah. It means that so in this on this particular sphere P and Q there is no time variable, right? It's implicit. It's going to it evolve in this way. You don't see the time exist, but when I put this time exit, you can see that actually this thing is going to be kind of map, kind of projection back somehow. This kind of thing. Is that clear for you? Okay. And of course that according to Liouville theorem, you could say that you have this kind of relation. Okay, right. It means that the number of points in the area 1 is the same as number of points in the area 2. Okay, and so let's have a look for the thermodynamic system. For the ideal gas, you have this kind of surface. And what I'm going to look at is for the adiabatic process, because for this side, the Hamiltonian is constant, right? Along this line, we need a constant energy or a constant Hamiltonian, and then we also need a process that involves actually constant entropy, right? And the process actually, your entropy is constant in adiabatic process. Right here is, sorry, where is let me point here. This is a adiabatic process, which is actually your S is constant, right? And actually there is a lot of process that you can draw, right, from this point to this point, right? But this is isothermal process right here. Okay, so it means that if you extend your space for P and V, and then you extend into the T direction, which is actually the same with this side, you will get this kind of surface. And then once you project this surface back into this 2D diagram, you will get this picture. But in 3D case, you will get kind of curvy surface here somehow. Okay. All right. So I would say that this would be the surface of constant entropy. Okay, because in all and this kind of projection somehow. Okay, so suppose that actually it's the same. That actually we have 1 and 2 here. We're going to have 1 and 2 here. All right, actually going up in this way, right here, because the temperature starts from this one and to be this one, right? It means that the number of points at again, number of points in the area 1 should be the same with the area 2 according to the Liouville theorem, right? And again, if you extend into the 3D surface, you're going to have this one, and you're going to have this relation, right here, according to Liouville theorem. Okay. Okay, so now we kind of ready to say that actually somehow we could construct the equation of motion for this thermodynamic process by having this kind of structure. Okay, so for the adiabatic process that actually start from 1 to 2, right? And this particular line, there is a particular temperature, right? A constant temperature to another constant temperature here. And we know that for the adiabatic process, the entropy can be captured in this way. And the gamma is the ratio between the Cp and Cv, and for the ideal gas is nothing but 5/3 from here. Okay, and you just plug your S into this Maxwell equation. You can solve equation, and you get these two equations, which is actually nothing but another two relation you could get for the ideal gas for the adiabatic process somehow. Okay, so it means that in this case your temperature going to play a role of independent variable, right? You see, because your system starts from this and evolve along this line, right? And temperature change along this line. Okay, so that is the thing. Then more or less that actually now we kind of have more or less the same terminology that we could say that now we can explain thermodynamic system with the equation of motion, right? But it's a bit, you might say that it's kind of weird, but yeah, according to structure, I would say that, well, we have more or less the same that we have in the Hamiltonian one. Okay. So that's it. Sorry. So let me summarize what I have so far. So we kind of successfully formulated the Lagrangian description to capture the part-independent feature, right, of the thermodynamic potential. That actually the working example is nothing but the internal energy, right here. The main point is that, as I mentioned, the standard Lagrangian formalism is not enough, right? We need to extend, we need a Lagrangian one-form structure to capture the part-independent feature, right? But if you don't care about Lagrangian, you can say that actually there is already part-independent feature, right? But if you want to capture in the Lagrangian sense, you need Lagrangian one-form structure. Okay, and this kind of the whole thing, the whole process that I explained, it can be explained on this kind of very fancy space that we call context space, and actually we can project to the particular space that we call equilibrium one, associated to the equilibrium of the system. Yeah, right, as I explained earlier. Okay, and also there is some symplectic structure associated with it, right? Yeah. And so we also have kind of, it might not, I don't want to say successfully, but yeah, I put it already there. But actually, we can somehow construct the way to explain the thermodynamic process in the same sense that we have in the Hamiltonian setup somehow, okay, by matching this kind of the structure of a set of variables from the Hamiltonian mechanics and the thermodynamics right here, and this one. And by working on that, we're going to get this kind of set of equation out of that kind of analog of Hamilton equation, but in the thermodynamic sense, on the Maxwell equation. Okay. So yeah, as I mentioned, the working example is just very simple, like ideal gas, right? Then it would be good to explore further on like a real gas or like a reversible process, something like that. Okay. Okay, open problem. So can we have like a Lagrangian analog for this structure? That is the question. Yeah. Can we, I don't know, well, the question might not trivial because you have to understand that actually the Lagrangian structure that actually that we have for this is very implicit, right? It's kind of very abstract way. It's very implicit. But what I mean by having Lagrangian in this context is not implicit, but it must be explicit somehow. Okay, but I don't know. We need to work out on this. And what about non-equilibrium system? We don't know about that. We need to explore more. And can we quantize the thermodynamic system? That is a main question here. Because we know that actually, if you want to move from classical mechanics to the quantum one, right? You can start from having like Hamiltonian mechanic space, right? Hamiltonian mechanics, and you operate thing to be the operator somehow, and you could work out, and then everything you get quantum version of your system. Then the question is that now we have more or less a kind of the same structure with the Hamiltonian, right? Can we can we promote it to be like an operator, or can we quantize it somehow? And what kind of thing that we could get from this kind of thing it might sound a little bit weird. But what I had in mind is actually I need to make sure that actually you really understand what I mean. So normally you have thermodynamics, right? And you can go to the classical mechanics, and then you can go like quantum statistical mechanics, right? In this route, right? And then it means by having this, you need to combine from this to this. You need to put quantum mechanics, right? With the classical mechanics, you get this one. And from this, you can have what they call quantum thermodynamics here. But the definition of the quantum thermodynamics in this sense is not what I want, right? Because this is the definition actually I get from ChatGPT, right? It's kind of the field that studied the explore interplay between quantum mechanics and thermodynamics. Yeah, it seeks to understand how classical thermodynamics concepts such as heat, work, entropy, temperature are modified or reinterpreted. When quantum phenomena come into play, this branch of physics is particularly relevant for understanding behavior of small systems, right? That kind of thing. But what I have in mind actually is that this by this having this root, as I explained, that actually we have the Hamiltonian dynamics in thermodynamics now. Then we have this kind of Poisson bracket. The question, can we promote it to be like an operator here? I put this epsilon here because normally in the standard Hamiltonian dynamics, you could have P and Q, right? And once you promote, it's going to be like an IH bar here. But for this P and V, the dimension of these two are going to give you like an energy unit, right? It must involve some other fundamental constant that actually give you the energy unit. Then I don't know yet what it is, right here. And again, what I had in mind is actually in this way, not in this kind of context here. But I don't know. Once we have this, can we go up to this? I don't know at the moment. And then furthermore, if we have Lagrangian dynamics, the question we don't have yet at the moment. And if we have, can we have kind of some possible part of what? I don't know. Again, that is kind of open problem so far. Okay. Okay, I just stop with this kind of, I like this course from the Quantum magazine. Can thermodynamics go quantum here? I think this is quite very entertaining stuff you can, if you want to read, I think. But there is some bit actually I kept from the web page actually. Quantum thermodynamics first start being thought about during 30, right, and then quantum engine was proposed around this time, and there was work in 80, but this piece of work were not always accepted by wider community, and quantum thermodynamic itself was sometimes called an oxymoron somehow. You know what it means, oxymoron somehow, because thermodynamics was developed for large classical system, so people just couldn't understand what it could possibly have to say about quantum system. It's kind of conflict in itself somehow, because you say when you talk about thermodynamics, right, it's kind of large system, and then when you put quantum in it, what does it mean? That's it. Thank you very much.
Any questions?
So for the Lagrangian one-form structure, it applies to any system or just to some of the systems?
You mean for other potential, right?
Yeah, probably.
Yeah, of course that for some, I'm not sure what you mean by system, but by having this, sorry. I mean, I start from this internal energy, right? And then I just do things in this way. And of course, we can start from Gibbs free energy or Helmholtz one and do the same. Oh, sorry. Sorry, this is bad again. And you can, of course, have this kind of structure, but the stuff inside is different. Right.
Well, actually, I mean, in the classical mechanics, do you use the Lagrangian one-form structure or just the standard?
In the classical mechanics, yes. Right? Yeah, it depends on, again, in the standard context, you don't need Lagrangian one form. Like if you're working with the free particle or the harmonic oscillator, you don't need that. But you need this kind of structure when you have a system that actually like an integrable system that actually there exists a set of Lagrangian, that actually this set of Lagrangian come with extra feature that you need this kind of one form structure to cope that kind of feature. That's it.
But in order to have the analogy between classical mechanics and thermodynamics, do you need the Lagrangian one form structure or just any standard classical mechanics in your form?
Okay, good question. By doing this, I just capture the part independent feature of the thermodynamic function in terms of the Lagrangian description, but I haven't working out yet with this kind of analogy that I explained to you here. I don't have the Lagrangian description yet for this one, but in just captured part independent feature, I say that actually we can use the Lagrangian one form to capture that. If you want to expand things in the Lagrangian.
I'm a bit confused with the part dependent feature in the classical mechanics. I mean, I believe that you define dA equals to T dQ minus H dt, right?
Sorry. It's I need to go backward, right? Sorry. Where is it? I think maybe around somewhere here. This one, right?
Yes. Yeah. For example, this also applies to say free particles, right?
Yeah, of course. Yeah, I think yeah.
So I'm wondering what is A in this case?
A.
Yes. In the case of free particle.
This A.
Yes. Because one would expect it to be like Q dot square or something, right? But it seems there is no Q dot in
What is
the space variables.
The A variable here.
Yeah, I mean A depends on just only Q and T, right? In this case.
Yes, because if you say that now we're working with the free particle, this H is nothing but the P square or O2.
Yes.
Right.
Yes. And then normally the Lagrangian we would expect it to be something like Q dot square over 2. But then A seems to only depend on Q and T, but not Q dot. So that's a bit confused.
Well, it's not really it's not this is actually this is kind of the one form of the action somehow, and I'm not sure that I get your question really because this is nothing, but it's I think this is not the Lagrangian somehow. It's because it's not yet that kind of thing because you expect that you would get Q dot square out of this, right?
Yes.
Yeah. Of course that. Yeah. If you put the Hamiltonian in this formula, of course you will get Q dot square. Yeah. You need of course that you need actually to say that actually your P is actually I think
P is Q dot, right?
Yeah.
So say that P is Q dot, but then there is gonna be a problem with the next slide, I think.
Mm-hmm.
Yeah, P is partial A by partial Q at fixed T.
Mm-hmm.
Then how I don't know how do we get the Q dot on the right hand side?
Q dot.
Yes, because we would expect it to be like P equals to Q dot, right?
Yes, of course that we could have that if we go further a bit. This is my Q dot here. This is my P dot, right? This is my Q dot here. But as I mentioned, this is typo, right? This should be A. Sorry about it, but yeah, you could get Q dot definitely from this kind of structure, but it's a bit tricky because you start with kind of one form of the action. It's not directly. I'm not sure. Is it what I don't know? This is answer your question yet?
Not quite yet. Maybe we can discuss.
Yeah, sure. Okay. Okay. เอามาให้นิดนึงไม่มีอ่ะไม่okay. So sorry. This one. Okay, just want to have a look. Okay. Yeah, that's it. I don't know. Or do you understand the question, Pam?
discuss later.
Okay, right, okay. Yeah.
Maybe for your analogy on the path independent feature, that your analogy each variable in classical mechanics and variable in thermodynamics, like the table you present the table one that there is a slide that you present the table.
This one?
Yeah. I just wonder. I mean naively. So in classical world, like the time is also you can consider time as independent variable, but I mean in reality time cannot go backward.
Yeah, sure.
Yeah. But in this sense, I mean there is no restriction for the thermodynamics.
Well,
Space.
actually, let's say that actually, in the classical world, actually you can work with the plus t and the minus t. There's no problem with that. Is that right?
I think he means the way time will flow. Yeah, the way time flow. The dt should be.
Or you mean that the system should progress in only forward in time, right?
I mean, just in my opinion, because we are because you said that you compare like the analogy between two systems which have path independent feature, right? Why not compare like T with, for example, S? As well? I mean, if you go back a little bit one slide, that you compare.
Is that this one? More?
That
Which one?
Which one that you compare? Which one that you compare the path independent?
Very it's at the beginning, I believe. No, it's too
big.
Where is it? Interesting. I couldn't find it. This is the first one. Actually, I have a table, and actually this one. I also
probably too far. Maybe let's go back a little.
This one?
A little. A bit. Yeah. Okay. Let's see by this. Okay. Because you have the part when TDS minus PDV, and you mentioned that it would be zero, right? So, and you compare it with like another set of equation.
I compare
PDQ. That one. That because of the color.
Sorry, my bad again.
I don't see
My bad again. It's kind of hiding there. Okay.
Yeah, like PDQ minus HDT. There. I mean inverse. I mean, like, can you compare like T with H instead, but with the minus sign? I mean, you can. Could it possible that you can redefine your variable like through like dA to the minus dA or something that you can compare T with S? Is it make more sense? I mean, dt is such that dt would, if you consider like the macro state, like dt go positive and ds go positive as well.
Oh, okay. I kind of get your point. But yeah.
And if you compare in this way, I believe that your boson bracket doesn't change because. Or is it? I don't know.
I think it's going to change. I believe because what I match the particle between the particle particle is no. Sorry, why I speak Thai? But anyway, I match between the variable from the Hamiltonian and thermodynamics. If you change, it's going to affect of course the prolonged structure, I believe, because now we have this pair, right? You get this boson. Yeah. If you have this pair, you have this one. But if you want to change S to be what?
S with T. If you change with S with T.
With big T.
S.
V. Right. With the V, right? I believe. Okay, let's get back to. Sorry.
Okay.
This one.
So for the, if you compare it directly, so P would be interchanged with capital T, which is temperature, and Q.
Mm-hmm.
Yeah, and Q with capital S.
Q
with capital. Okay. Yeah, but if you like maybe a little bit redefine your variables.
Yeah, you mean that I just add the minus and the minus here?
Yeah.
Okay. And plus the minus here, something, and then
it doesn't make it doesn't change like the path independent property if you add.
I think so. Yeah, it's just kind of. Yeah, I think so. Yeah.
So it's such that you can redefine T with capital S and H with capital T. Right.
Yes.
So that T and H would be on the same footprint. I mean, on the same level or Poisson bracket in the same way.
Oh, right. You mean you want to move this to copy and this to variable to this one, right? And this move this back to this. Is that what you say?
Yeah, probably I'm a little confused.
Yeah, but I can get your idea. Okay, I see.
I don't know what is it gonna be like make more sense in that way? I'm not sure.
Yeah, I don't know either because I just play with the math and I don't really have carefully think about physics much. As you mentioned, actually, your point is very interesting because normally the system, the classical system, like we have like going to evolve forward in time, right? But the variable in thermodynamics can be, does not obey that kind of rule somehow. Yeah, but what I present here is just try to say that actually there is kind of analog structure that we have in Hamiltonian mechanics and the thermodynamic system that is. And of course that we are not yet complete everything. There's still a lot of things that we don't understand and we need to explore further, of course. But your point is very interesting. Because of course we can play a little bit with that kind of trick, I would say trick math, and then we can solve things, and then of course. Thank you very much. Yeah. I think
Any questions?
So could you please move
forward and backward?
forward?
Okay, forward. You are classical system, right?
Huh?
You classical system, right? Because you need only forward. Okay, which one? Which slide? More?
Free what? Free.
Huh?
ไอ้หน้าที่มันมีP เท่ากับอะไรหรือเปล่า
Okay.
Yes. When you compare time temperature together, I feel like a bit confusing.
This one.
I think it's, but anyway, normally we can obtain the particularly in like classical mechanics, very reaction. So it is possible to identify the Lagrangian first and then vary, or even like give it the general expression and then with respect to
The coordinate, that's
but it seems like in the thermodynamic case, it's like cheating a bit, right?
Yes,
Because you cannot identify. Like,
it's kind of depend on the process that you're working with.
yeah.
Yeah, of course. Yeah, that is a point. Yeah.
So it means that temperature that you said that it is like at the level at the same level as time. It depends on the way you choose the. It's like you said that the participatory you can obtain by identify the what called อุณหภูมิของที่มันเป็นชื่อ
Isothermal process.
ประมาณนั้นอันนั้นคือมันเหมือนเราไม่ได้ vary แต่เราเป็นเหมือนเราระบุคุณสมบัติของผักนั้นขึ้นมาแล้วเราก็บอก
Right. I kind of get your question. If I get wrong, please say it again. Well, we need to get back to this structure because I start to compare the left hand side and the right hand side. If you see that, what I bring here for the Maxwell equation here, these two equations, this entropy here going to play a role of like the Hamiltonian in the classical mechanics. It means that the process that I need to work with is in the process that actually the entropy is constant. That is kind of constraint. That's why I need to consider the adiabatic process. And of course that you can, of course, I don't know. I don't have worked it out. I haven't worked it out yet. But I mean that in general, you could say that there is a point here and then some kind of arbitrary path, right, that go to this point. And then you can say that actually there is some kind of action and then you vary, you could get that kind of set equation, right? Yeah, I think you need that kind of thing, right? That new question, right? Yeah, of course. But we need to, well, as I mentioned, we need to be careful here because it depends on the structure of the Maxwell equation. And also the process that actually involved with that kind of set of Maxwell. At the moment, my answer is this. But in the future, it might not be this one because so far I just this is my understanding so far. Yeah, we haven't worked out further yet. But of course, it would be very good if we could have kind of general scheme. That to work it out, that kind of thing, some kind of the arbitrary part on this, and then you can map like something like that. Yeah, we don't have yet that kind of thing. Oops, sorry. Any more questions? Okay. Online question. Oh, yeah. Within QFT, some Euclidean system are periodic equal to inverse temperature. How can we interpret it with analogy between temperature and U you show? I don't know, to be honest, because yeah, of course that you. Sorry about that. Because you mentioned about QFT, you two have any idea? To be honest, I don't know at the moment, but it's very interesting. But let me emphasize again that actually the system that I work with is just very simple classical mechanics, classical system both in the classical mechanics and also in the thermodynamics, but we don't have the quantum version yet. That kind of stuff for the thermodynamics, and I could not answer your question at the now. I think, but I don't know. In the future, might possibly or might not. I don't know. Yeah. Thank you very much for your question. I think that's it.
Okay, if there is no further question, I would like to say thank you to speaker. Thank you very much for speaking.
Okay. Yes, I was speaking. Yes. Okay. ขอบคุณครับ
Thank you.